So the very last thing that we talked about was the idea of having a balanced chemical equation. This is one that'll have the exact same number of each atom on each side. So you can't change one type of atom into another, and you can't take away or destroy any atoms. So you cannot balance an equation by changing the subscripts, because if you change the subscripts, for example, H2O to H2O2, you'll change the identity of the substance and you'll change the whole nature of the reaction. You can only change the coefficients, which are the numbers in front, and tell you how many of each element or compound is present in that reaction equation. So here's 3 steps, and this is on top of page 89. For balancing in the equations, first of all, you're going to change the coefficients of compounds before elements. The reason for this is if I put a coefficient of, say, 2 in front of this carbon dioxide here, that changes the number of carbon atoms and the number of oxygen atoms. Whereas if I put a 2 here in front of oxygen, it just changes the number of oxygen atoms. So you want, if you have any elements present, that to be the very last thing you balance, because when you put a coefficient there, it's not going to mess up any of your previous work. So if you have any elements, save that balancing for last. Next, you're going to treat any sort of polyatomic ions that are on both sides of the equation unchanged as individual units. So for example, if you have a carbonate at the start of the equation and carbonate also occurs at the end of the reaction, you're going to just count how many carbonate units. Now when you do that, do not count it doubly. So don't count how many carbonates and then also count how many carbons and oxygens. It's one or the other. And it's a whole lot easier just to count the polyatomic ions. And then every time you change a coefficient, you need to update your count. So update how many you have of each element. So we're going to try out a couple of simple ones and then work our way up to a little bit more complicated of a reaction equation first. So the first one I'm going to do, nitrogen plus hydrogen makes NH3. What's the common name for NH3? Ammonia, right? So this is the synthesis of ammonia. This is called the Haber process, named after the scientist who discovered a way to industrialize this process. So I started with this because it's nice and simple. You might even be able to do it in your head, but we're going to go through all the steps as though you can't do it in your head. And then as it gets more complicated, if we follow those steps, it'll make it easier. So we have reactants on one side of the arrow, products on the other. So I'm going to write every element, or polyatomic ion if present, down right here underneath the arrow. So in this case, I just have the 2 elements, nitrogen and hydrogen. And then I'm going to keep track on either side of how many I have of each element. So on the reactant side, how many nitrogens do I have? 2. How many do I have on the product side?
1.
Just 1. Hydrogen, how many do I have on the reactant side? 2. How many do I have on the product side? 3. So in this case, both nitrogen and hydrogen are present as elements. So it doesn't really matter which one we balance first. Let's just balance nitrogen first because it's the first one up there. So I've got 2 nitrogens as a reactant and only 1 on the product side. So I need a coefficient in front of ammonia that will fix that. What coefficient will fix that? 2. Now, when I distribute that 2, I now have, instead of 1 nitrogen, 2 nitrogens, but it also changed the number of hydrogens. Now, how many hydrogens do I have? 6. Good. So now nitrogen is balanced, hydrogen is not. So what coefficient in front of hydrogen will balance that? 3. So now I have 6 and 6, and now I am balanced. So again, that's pretty simple and straightforward, but that's how to balance an equation. Questions about that one? Let's try one. It's got.
For 6 hydrogen,
Mm-hmm.
do you multiply the 3 hydrogen, the 3 H2?
So 2 times 3 is where this 6 came from. And then 3 times that 2 is where that 6 came from. Let's try. So I'm going to jump to a sample problem real quick, and then I'll go back and do the problem that they have on the slides, because I think the sample problem is ironically easier than the one in the slides. So here's the sample problem 3.3 on page 90. Now, in this question, we already have the setup for what the compounds are just to save time today, but as you would be given this on a homework or test question, likely you would only see this top paragraph here, which says to write out the equation, and it gives you the names of the compounds, which means you have to remember from chapter 2 how to go from the name to the formula. So in this case, we're told, write and balance the chemical equation for the aqueous, so our state of matter is AQ, reaction of barium hydroxide, so barium hydroxide is BaOH, and there's 2 hydroxides to cancel out the charge of 2 plus on barium, and perchloric acid. So perchloric acid is based on the perchlorate ion. So perchlorate is ClO4, it has a 1 negative charge, so we have just 1 hydrogen. So there's our perchloric acid. To produce aqueous barium perchlorate, so there's our barium perchlorate. And water of course can't be aqueous because aqueous means dissolved in water. It's just going to be a liquid. So the problem is this is not balanced. So what we're going to focus on right now is how to add coefficients to balance this equation. We're going to do the same steps we did before. Now it looks like a whole lot more than the last problem, but what's going to help us here is that idea of using polyatomic ions on both sides when we are balancing. So first of all, I'm just going to go in order that they appear in the equation. The first element is barium, so I'm going to write a Ba here for barium. Next, hydroxide. Hydroxide is a polyatomic ion. Is it on both sides of the equation, though? No, there's no hydroxide on the product side. So that rule of using polyatomic ions as individual units, we can't use that for hydroxide, so we're going to go ahead and have to break that apart into its oxygen and hydrogen. Next, we already have hydrogen, but the perchlorate, does perchlorate appear on both sides? Yes, ClO4 perchlorate does appear on both sides, so I'm going to write that down as a unit. Now when I count on both sides, how many of each I have? Barium. How many bariums do I have on the reactant side? 1. How many on the product side? 1. Oxygens. Now, when I'm counting up oxygens, I'm not going to count any of the oxygens that are inside of the perchlorate because they're taken care of. I'm only going to count any that are not inside the perchlorate. So how many oxygens are on the reactant side? 2. I have 2 hydroxides. Each one has 1 oxygen, so there's 2 oxygens. On the product side, how many are there?
1.
Just 1, just the one in the H2O. Hydrogen, how many hydrogens are on the reactant side? 3. Good. There's 2 from the hydroxide and 1 from the acid. How many hydrogens on the product side? 2. Perchlorates, how many perchlorates do I have on the reactant side? 1. I just have 1 perchlorate. How many do I have on the product side? 2. That's what that subscript of 2 means. I have 2 perchlorates. So that is our setup. Now we don't have any elements by themselves, so we'll just go from at the top and work our way down. So first of all, barium, is it already balanced? Yes, because barium is already balanced, it would probably be helpful to try and avoid changing the coefficients of either of the compounds that have barium, if we can avoid it, because then that would mess up barium being balanced already. So next, looking at oxygen. Oxygen has 2 on the reactant side, but only 1 on the product side. So what coefficient and where will fix that? Good, 2 on the H2O. So I put 2 on the H2O, now I have 2 oxygens. But that also changed my number of hydrogens. Now how many hydrogens do I have? 4. Now hydrogen's not balanced, and neither is perchlorate. At this point we can try and figure out hydrogen, or we can try and figure out perchlorate. Honestly, probably a little bit easier to look at perchlorate real quick, because 3 and 4 versus 1 and 2, 1 and 2 sounds a little bit easier to balance. And it might just fix everything. So perchlorate, I have 2 on the product side, but only 1 on the reactant side. So what coefficient and where will fix that? 2 in front of the, which reactant? Perchloric acid. 2 there. Now I have 2 perchlorates, but what else did that change? Hydrogen. So now how many hydrogens do I have? 4. Good. I have the 2 from the hydroxide, and now I have 2 from the acid for 4. So now am I balanced? Yes. So how bad was that to balance? Not so bad, right? It looks scary at first, but it ended up, if you just take it bite by bite, step by step, break it down, didn't end up being so bad. Any questions about any of those? All right. Let's try a different kind of problem. Combustion. Combustion is a chemical reaction. What does it mean if something combusts? Does what? Flammable. It reacts. So if it's flammable, it bursts into flame. What are the 2 things that a fire needs? Oxygen and fuel. Good. Oxygen and fuel. Now in this case, we're going to talk about the combustion of hydrocarbons. So our fuel is going to be a hydrocarbon, so carbon and hydrogen-based compound. The products, therefore, of a combustion are carbon dioxide and water. So here is our reaction. We have C4H10. Anybody remember from chapter 2 what C4H10 was? Methane was 1 carbon, ethane was 2 carbons, propane was 3 carbons. Anybody remember what 4 carbons was? Give you a hint, cigarette lighters. Butane. Good. So this is the combustion of butane. So it reacts with oxygen. Fire needs oxygen to burn. The products are going to be carbon dioxide and water. So this is a combustion reaction. So I'm going to, rather than use what they've got there, I'm going to rewrite this equation on another slide where I have lots of space. Now it's right here. C4H10 X with oxygen, make CO2 and H2O. So there's our combustion of butane. Now in this case, I do have something that's an element. So what is the last? We have 3 elements here, carbon, hydrogen, and oxygen. What's the last thing I should balance? Oh, oxygen, because it's an element by itself on the reactant side. So I'm just going to write them down in order. Carbon, hydrogen, oxygen. Same as before, we're going to list how many we have on each side. So carbon, how many do we have on the reactant side? 4. How many do we have on the product side? Just the 1. Hydrogen, how many on the reactant side? 10. How many on the product side? 2. Oxygen, how many on the reactant side? 2. How many on the product side? 3. Good. It's in both carbon dioxide and water. So what do you think the first thing is probably going to want to balance here? Which element? Carbon. So how can we balance carbon? Good. Multiply CO2 by 4. So I'm going to put a 4 here, and now I have 4 carbons. What else did that change? Oxygen. What's oxygen up to? 9. Good. Everybody see why it's 9, not 8? 4 times 2 plus you still have the 1 from the water. 9. All right, next, hydrogen. What coefficient and where can fix hydrogen? 5 in front of the H2O. Good. Now, so now I have 10 hydrogens. What else did that fit to change? Blech. Oxygen. So now what's oxygen up to? 13. Good. 8 from the carbon dioxide, 5 from the water, for a total of 13 oxygens. Now here's where we have an issue. A balanced chemical equation uses whole number coefficients. I need 13 oxygens. On my reactant side, I have oxygen present as an O2. Can you get an odd number of oxygens from O2? Not using a whole number. We can't get it using a whole number. So there's two different ways of going about this. One is just keep on ramping up, ramping up, ramping up, ramping up, which is kind of time consuming. Another one that's more preferred is to temporarily use a fraction. Yes, oh my gosh, fractions, don't get scared. It's a fraction, but we're going to get rid of it by the end. It'll be gone by the end. So we would need to know what fractional amount of O2 will give us 13 oxygens from an O2. Let's use it as a compound fraction. 13 over 2. Okay. So 13 over 2 is a fraction. 13 over 2 times 2 gives us our 13 oxygens. So at this point, we are technically balanced, but it is technically not a valid balanced equation because we've got a fraction in there and we need it to be a whole number. So now let's get rid of that fraction. Change color. To get rid of a fraction, you have to multiply by what part of that fraction, the numerator or the denominator? Denominator. So in this case, the denominator is a 2. I'm allowed in algebra to multiply something by a coefficient as long as I do what? Good. Multiply both sides by the same coefficient, which means I'm going to multiply this whole thing by 2. So that 2 is going to get distributed to everything in this equation. So 2 gets distributed to the methane. So now I have 2 C4H10s. 2 times 13 halves is how many? 13. Good. How many carbon dioxides? And how many waters? 10. Make sure that you are still in the lowest whole number ratio. A balanced chemical equation is in its lowest whole number ratio. So if these coefficients are all divisible by the same number other than 1, then you need to simplify it. This is another place where students don't understand why they get something wrong and connect, is where they have, it's balanced, but they were all divisible by 2, or they were all divisible by 3. It's not balanced if it can be reduced. So I have coefficients of 2, 13, 8, and 10. Are those reducible, or is that the lowest whole number ratio? It's the lowest whole number ratio. Now we're going to double check our work, make sure we did this right. Always double check your work. Carbon, hydrogen, oxygen. Now, how many carbons do I have on my reactant side? 8. Good. 2 times 4 is 8. How many do I have on my product side? 8. How many hydrogens do I have on my reactant side? 20. 2 times 10 is 20. How many do I have on my product side? 20. 10 times 2 is 20. How many oxygens do I have on my reactant side? 26. All right. Now, on the product side, how many do I have from the carbon dioxide? 16. How many do I have from the water? 10. So 16 plus 10 is? 26. Are we balanced? Yes. That's like the hardest balancing problem that I would give you, which is why I'm not quite sure why your notes thought it was the appropriate first example. Like, this is as hard as it could get. Now it'll get easier. So if you end up in this case where you have an odd number you need, but you can only get an even on the other side, temporarily use a fraction. Just don't forget to get rid of it at the end. Double check your numbers. Make sure you're in the lowest whole number ratio. It's not reducible. Make sure that you are still balanced by counting up your total numbers of each element. Sound good? All right. Let's try one more example. Assuming that the only products are carbon dioxide and water, write and balance the equation for the metabolism of butyric acid, given the formula of butyric acid is C4H8O2. So metabolism, what do I mean by metabolism? What kind of a process is metabolism? I know you've heard that term. Yes?
Converting one type of energy into like a type of energy that you can use, like photosynthesis.
Mm-hmm. So producing energy from some sort of stored energy, right? So where does metabolism occur? In humans, right? Living organisms, in our cells. Metabolism is a biological, biochemical reaction. It occurs in our cells. We take in food sources, we metabolize those to produce the energy, which is why if you don't eat all day, you feel sluggish, right? You don't have any energy. So this is butyric acid. Notice here's the equation for butyric acid. Butyric acid reacts with oxygen to make carbon dioxide and water. Now, what kind of a reaction does that look like? Combustion reaction. In fact, it is combustion just without the fire. So when we take in food, what is the energy unit that we count our food intake in? Calories, right? And then when you are metabolizing, whether you're just sitting around metabolizing or you're running on a treadmill metabolizing, what does your body do to those calories? What's the term we use? Burn them, right? We burn calories. That's because it is the exact same chemical reaction as combustion. Now, does combustion release heat or take heat? Releases heat, right? Fire hot. We know that one. When our bodies metabolize food, do you think that it releases heat or absorbs heat? Releases heat. Yeah, that contributes to us being, warm-blooded, having heat in our bodies. As part of that is metabolism, this kind of reaction. So, even though it looks like combustion, and it kind of technically is, there's no flame here, but we need two things. We need fuel, and we also need oxygen. Kind of hard to metabolize if you're not breathing. That's why if you're working out, you have to breathe more, right? All right, so back to the question at hand. Let's go ahead and balance this. So it looks the same as the last problem. Carbon, hydrogen, and oxygen. We're going to balance the oxygens last because it's the element by itself. Hydrogen, oxygen. How many carbons did we start with? 4. How many did we end with? 1. How many hydrogens did we start with? 8. How many did we end with? 2. How many oxygens did we start with? 4. How many did we end with? 3. Good. Now you guys try on your own to come up with coefficients that will solve that problem. Don't worry, it's easier than the last one. All right. So, what is our coefficient in front of the butyric acid? How many of those do we end up with? Just 1. So if it's just 1, we leave it alone. You don't have to put a 1. How many oxygens do we end up with? 5. Good. How many carbon dioxides? 4. And how many waters? 4. Anybody not get that? Yes. So when let's go ahead and update these numbers down here. So carbon, when I put a 4 in front of carbon dioxide, that became 4 carbons, and it changed my oxygen into 4 times 2 and 4 times 0, so 8 plus 4 is how many? Sorry, 4 plus, how many? 12, right? 4 times 2 is 8, plus 4 is 12. Hydrogen, 4 times 2 is how many? 8. Now on this side, I have 2 oxygens from my butyric acid, and 5 times 2 is 10. So 2 plus 10 gives me 12. Always double check your work and make sure it's still balanced. So a common mistake I see here was instead of putting a 5 here, putting a 6, because you said, oh, I need 12, and that's because you forgot that there were still already 2 oxygens here. So you only needed, even though you needed a total of 12, you only needed 10 more because you already had these 2. All right. Moving on to the next section. So the next section we're going to talk about moles and converting between moles and grams, grams and moles. And then empirical formulas. We learned how to find the empirical formula from the chemical formula in the last chapter. Now we're going to learn how to find the empirical formula from experimental data about the percent composition. So we did on Friday an assignment where we were learning about how big a mole was, where you were counting out the beads. So how big did that mole end up being? A mole of beads. How long did it take you to count out a mole of beads? Years. Not just a couple of years, but most people was around 10 to the 16th years. Is that a big number? Yeah. I mean, like compared to the life of the whole universe, right? That's a really long time to count out a mole of objects. So that's how big a mole is. Now again, a mole is a quantifier. It is not a unit unto itself, any more than you'd say to your friend, hey, can you go to the store and get me a dozen? They're waiting for the second half of that. A dozen just tells them they need to get 12, but you still need to tell them 12 whats. 12 donuts, 12 cans of soup, 12 what? Same thing with a mole. You can't just say, I have 5.6 moles of what? That's just a quantifier. It doesn't actually tell you what the unit is. So a mole is 6.022 times 10 to the 23rd objects, just like a dozen means 12 objects. A gross is 144. A pair is 2, etc. So we call this Avogadro's number. The symbol for it is an uppercase A with the uppercase N with the subscript uppercase A. We're only going to use that to four significant figures, so 6.022 times 10 to the 23rd, but there it is to more significant figures if you are curious. And it is equal to how many atoms are in exactly 12 grams of the carbon-12 isotope. Now, the carbon-12 isotope, in Chapter 2, we use the carbon-12 isotope as a way of defining what unit. What unit is defined as 1/12 of a carbon-12 atom? AMU, good, atomic mass unit. So that's going to come into play a little bit later. That both atomic mass units and moles were defined from the same concept, a carbon-12 atom. So we can use this as a conversion, just like we did back to Chapter 1. So in chemistry is a quantitative science. The key to these problems, all these math problems, no matter how complicated they get, trust me, is always going to be the units. If you have a good grasp on the units, what unit you start with, what unit you need at the end, and then just how to convert units. Chapter 1, factor label method, or the railroad track method, whichever method you prefer to convert units. If you have a good grasp of converting units, then that will answer pretty much any of these chemistry math problems. So we, in Chapter 1, used factor label method, which means I have some factor. In this case, 1 mole of whatever our objects is equal to 6.022 times 10 to the 23rd. And we can rewrite this as a fraction, either 1 mole on top or the 6.022 times 10 to the 23rd on top, where these fractions are both equal to just 1. So multiplying by them just changes the unit, doesn't change the quantity. So in our case, in Chapter 1, we learned that we picked which fraction by what we needed to cancel. The units cancel when they're opposite from each other. So let's look at a couple of sample problems here. A typical human body contains roughly 30 moles of calcium, mostly where? Bones, right? Your bones are full of calcium. Now, so question number A asks, what is the number of calcium atoms present in 30 moles of calcium? And then part B asks us to go backwards. So part A, we have 30 moles of calcium. 30.00 moles of calcium. Now our factor here is 1 mole is equal to 6.022 times 10 to the 23rd. So there's the two fractions written either with the mole on top or with the atoms on top. from our factor here, when we say objects, in this case, our objects are going to be atoms. We pick the factor that's going to let our units cancel. So our unit is starting off as moles of calcium, which means in our factor it needs to be where, top or bottom? Bottom. If moles of calcium are on the top, they need to be on the bottom in our factor. That way they will cancel out. So that is which one, the first factor or the second one? Second one. Second one's got mole of calcium on the bottom. So that means 1 goes on the bottom, and 6.022 times 10 to the 23rd. Calcium atoms goes on top. When we multiply this then, because moles are opposite from each other, moles of calcium will cancel, and the unit we'll be left with is calcium atoms, which is what we're being asked for, the number of calcium atoms. So always double check that your units are making sense. So that should be a big number. What do we end up with? 30 times 6.02 times 10 to the 23rd. Yes? Times 10 to the 25th. And now our unit is calcium atoms. Make sure you know how to do scientific notation in your calculator. If you're struggling, please come see me after class, during office hours, or go to the Academic Skills Center and ask them for help. You see where this one comes from? All right, so next one a little bit trickier. Now, part B asks what is the number of moles of calcium in a sample containing 1.00 times 10 to the 20 calcium atoms. 10 to the 20, is that bigger than a mole or smaller than a mole? Smaller than a mole. So we should get some number smaller than 1. Should just get a number smaller than 1. Always make sure your answer makes sense. And it helps going into it before you start the calculation to get an idea, rough estimate of what kind of number you're looking for. That way, if the number that comes out does not fit your expectation, you can go back and say, okay, I must have done something wrong, and double check. All right, so in this case, now I'm starting with calcium atoms. 20 calcium atoms. So I'm going to multiply by a factor here. That has calcium atoms on the bottom so that that unit cancels. Which means now I'm looking at this factor. Calcium atoms on the bottom and moles on the top, because I'm being asked what are the number of moles. So the unit you want needs to be on top. Moles of calcium. So now 1 goes on the top and 6.022 times 10 to the 23rd goes on the bottom, which means we are basically taking our 1 times 10 to the 20th and dividing it by 6.022 times 10 to the 23rd. Should give us a small number. I'm getting 1.66 times 10 to the negative 4th. Getting that? And now we're in moles of calcium. That. Moles of calcium. There you go. Once you put that in scientific notation, that's 10 to the negative 4th. All right. So some people like using this like it's a unit conversion, so we're using the factor label method that we learned in chapter 1. Some people prefer a flow chart that just tells me, what do I do? Am I multiplying by Avogadro's number or am I dividing by Avogadro's number? Whichever way you prefer, so I'll go ahead and show you. I'll just open a new slide and write the flow chart. when you're going between moles and number of atoms. This flowchart's on page 95 off on this little side here. It's got two boxes, top and bottom, but we'll do it side to side. So we'll do moles. Moles in the box versus number of particles. Now these particles could be atoms, they could be molecules, they could be compound units like sodium chloride. So number of particles, whether those are atoms or molecules, in our second box. To go from moles to the number of particles, that's what we did the first one, 30 moles of calcium, how many atoms are there? We're going to multiply by Avogadro's number. Multiply by Avogadro's number. Again, Avogadro's number, 6.022 times 10 to the 23rd. To go backwards from atoms or molecules back to moles, that's what we did the second time. Now we're going to divide by Avogadro's number. So whichever way feels easier, more natural to you, as natural as chemistry can be for most people, use that way. Doesn't matter to me if you write it as a unit conversion with factor label method or you just either multiply or divide according to the flow chart, whichever way. But I will recommend that you always use units. And when you're using units to show how the units cancel, the units for Avogadro's number are going to be your particles, which are either your atoms or molecules, per mole. So mole is on the bottom. Keep doing that. And again, that little flow chart is on page 95. Of course, if I'm in a lab and I'm measuring out and I have a block of sodium and I want to know how many atoms of sodium are in that block, I can't just take that block, put it on a scale, and the scale tells me how many moles are there. How can I measure the amount of that sodium? Was I saying sodium? Whatever I'm measuring, sodium, calcium. What is it going to measure it in? Grams. So we're going to need another part of this flow chart. We're going to need to know, how do I get there if I start at grams? So next thing we're going to talk about is molar mass. Molar mass is the mass of 1 mole. Every substance has its own molar mass, which is what the mass is of 1 mole of that substance, whether it's a compound or an element, whatever the mass is of 1 mole of it. The symbol for molar mass is an uppercase curly looking M, the molar mass. And it's in units of grams per mole. So molar mass is in units of grams per mole. So because it's units in grams per mole, that's why we use it to convert between grams and moles and grams. Now, how do we find the molar mass? The molar mass, by definition, is the mass of the molar mass of 1 mole of carbon-12 is exactly 12 grams. Wait, where did we just see that? Where are we seeing that a couple times now? The definition of a mole. We also saw the definition of atomic mass unit. When we say carbon-12 has a mass of 12 what? What's that unit? Back in chapter 2, when we said carbon-12 has a mass of 12, what was the unit back in chapter 2? AMUs. So we're saying that a mole of carbon-12 has a mass of 12 grams, but we already know from chapter 2 that carbon-12 has a mass of 12 AMUs. So what, in other words, I'm saying is it's the same number, just with the unit changed. So an atomic mass unit is going to be the same thing as the molar mass. So last time we learned how to find the mass of a formula. We already know about atomic masses. If you need to know the atomic mass, you just look at the periodic table. For a compound, you add up those. That's what we did before. We did H2O. You added up 2 hydrogens and an oxygen. And we use the atomic mass units as the unit there. Now I'm saying you can also use the unit grams per mole. The number will be the same. So for example, calcium. If you look at calcium in the periodic table, calcium's atomic mass is 40.08 AMUs. Its molar mass is 40.08 grams. If I had water, H2O, and I wanted to know its mass, 2 hydrogens at 1.008 apiece, plus 1 oxygen at 16, rounded to 2 decimal places, gives me what number? 0.16. We've only got 2 decimals, so I'm going to put 0.2. Atomic mass units, or grams per mole, which means we can use this. This is the molar mass of water. We can use this to convert between grams of waters and moles of water. Yes?
That says 12.
So it's 1.02?
18.02 grams per mole. Yeah. 18.02, yeah.
That was close.
No. All right. So this is atomic mass unit. We learned last time we can also convert between atomic mass units and grams using the reciprocal of Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd. The reciprocal, or 1 over that, is 1.661 times 10 to the negative 24th grams. So that is a conversion factor you can use between atomic mass units and grams. It's just 1 divided by Avogadro's number. All right. So our flow chart that we did a minute ago was this half of the flow chart, moles to atoms. Divide by Avogadro's number to go from atoms back to moles, multiply by Avogadro's number to go from moles to atoms. Now we're going to add a second part here, or third part, technically the first part. If you start with grams, to get from grams to moles, we're going to divide by molar mass. Because if we start off with grams and we divide by molar mass, which is grams per mole, what happens to our unit? Good. Those grams cancel out. Dividing by 1 over mole is the same thing as just a mole, and we're left with moles. To go backwards from moles back to grams, we're just going to do the opposite, same as we did over here. Go backwards, do the opposite. So going backwards, we're going to multiply by molar mass. So here's where I have a lot of students get this switched. They start with grams, they want to go to moles, and they multiply by the molar mass. First of all, the units should not cancel if you do that, but you'll only know that if you write the units in your work. When students are not getting the right answer and they show me their work, they're saying, I don't know why I'm getting the right answer. 9 times out of 10, they don't even have any units written down, much less showing how the units canceled out. So yes, it may be a little bit tedious, but trust me, keeping track of your units is going to help stop a lot of those issues. Write your units for everything, show how they cancel out in your work. If they don't cancel out, that's your hint that you did it backwards. So let's try this out. Determine the number of moles of carbon in 10 grams of naturally occurring carbon, and then backwards, the mass of 0.905 moles of sodium chloride. So molar mass of carbon, if I look in the periodic table, it's 12.01 grams per mole is the molar mass of carbon. So I'm starting with 10.00 grams of carbon. So I'm starting here at grams. I want to go here, moles. My arrow says I need to do what? divide by molar mass. So that's exactly what we're going to do. 10 grams carbon divided by our molar mass, 12.01 grams per mole. Show how the units cancel. How do the units cancel? Good. Grams divided by grams means that grams cancel. 1 divided by 1 over mole means that moles come to the top, so now our unit is mole. 10 divided by 12.01 is what? 0.8326. Yeah. We got 4 sig figs in this number, so we'll use 4 moles of carbon. Not so bad. Not so bad, but if you can tell from the previous lectures, the difficulty level is probably ramping up a little bit, right? A little bit. In Chem 151, the difficulty level starts off kind of lowish, chapter 1, just unit conversions, and then it ramps up and it ramps up. The pinnacle for most students, they say, of the difficulty is chapter 4. So downside is that means it gets harder than this. Upside is chapter 4 is not even halfway through the semester, and then it'll start getting easier. So there's an, when we hit chapter 4 and you're like, oh my gosh, this is so hard, it will get easier, I promise. Most students find chapter 4 easier, or chapter 5 easier, and chapter 6 and 7 much easier. So, all right, now let's do part B. Take this and go backwards. Find the mass, or how many grams, of 0.904 moles of sodium chloride, so NaCl. So first of all, we need to find what is the molar mass of sodium chloride. So molar mass is going to be the same thing as the formula mass, just with units of grams per mole instead of AMUs. So we learned how to find the formula mass by doing what in section 1? Looking at the periodic table. So in this case, I have both sodium and chlorine. So I look up sodium, 22.99 molar mass of sodium chloride. Sodium is 22.99 plus chlorine is 35.45. I've only got one of each, so I'm just going to add them together, and that's where 58.44 comes from. Grams per mole is the molar mass for sodium chloride. So now what are we going to do with that molar mass and these moles? Multiply them. Good. We're starting at moles and being asked for a mass, so now we're going backwards. Starting at moles, going backwards to grams, our mass, so it says multiply by molar mass. So we're going to take that 0.905 moles of sodium chloride, multiplied by the 58.44 grams per mole. When we do this, what unit will cancel? Moles. Good. I have moles on the top versus here I have it on the bottom. So that means moles will cancel. The unit that's left standing is grams, which is the unit for mass, so we're good. So what mass do we end up getting there? Good. 52.89. We've got 3 sig figs in this number, so we're going to round that to 52.9 grams of sodium chloride. On the next slide, it's just written a bit neater because they typed it out, but the same work. Now this sample problem straight out of your textbook. This is sample problem 3.6 on page 97. So when you're looking at their worked out work here, when they write in molar mass, instead of writing that the molar mass is 58.44, keep on doing that. Grams per mole, they took this and dragged it all the way across and said per 1 mole. So that's what this is here. This is still grams per mole. They just made the whole thing the numerator. Same thing. I write it as grams per mole as 1 unit. They write it as the whole mass is the numerator, then 1 mole is the denominator. But it's the exact same thing. The units cancel the same way, doing the same thing. All right. So on our little flow chart here, we have gone from moles to atoms, atoms back to moles. We've gone from moles to grams, grams to moles. So what do you think we're going to do next? Grams all the way to particles. So to go from grams all the way to particles, whether that's the atoms or the molecules, you're going to have to jump twice. So do 2 things. So if we start with grams and want to go all the way to atoms, we're going to have to first jump to moles and then jump to the particles. Let's try that out. So this is still the same page, page 97, but now we're doing the second sample problem. Part A says determine the number of water molecules and the number of hydrogen and oxygen atoms in 3.26 grams of water. 3.26 grams of water. Come on. So I'm starting at grams and I want to get all the way to molecules. So I'm going to have to jump twice. The first jump is going from grams to what? Moles. So how do you go from grams to moles? What's the step? Divide by molar mass. So anybody remember what the molar mass was for water? Good. 18.02 grams per mole. And again, that came from 2 hydrogens at 1.008 apiece plus the oxygen at 16. Then rounded to 2.466. So now grams will cancel. Grams cancel, grams cancel. At this point, we're at moles. I'm getting 0.1809. And now I'm at moles of water. So now that I'm at moles, what's the next jump? Good. Multiply by Avogadro's number. That will take us to the particles, which in this case, what's our particle? Are we at atoms or molecules? Molecules. Good. H2O is a molecule. So times Avogadro's number is going to be molecules per mole. Moles per mole. Do that. Now moles cancel, and we'll be left with molecules of water. I'm getting 1.09 times 10 to the 23rd. And this is now molecules of water. Everybody still with me? So now I'm at molecules, but it also wants to know what the number of hydrogen and oxygen atoms are. So to get from molecules to atoms, we're going to use the ratio. So, factor label method, chapter 1. What I want goes on top. What I don't want, what I want to cancel, what I started with, goes in the bottom. I currently have molecules of H2O, so H2O is going to go on the bottom. Let's do first hydrogen. I want hydrogen on the top. What is the ratio of hydrogen to H2O? 2 to 1, right? So the ratio here is going to be 2 hydrogens to every 1 water. When I do that, molecules of water cancel out, and I'll just be left with atoms of hydrogen. So whatever that number is times 2, 2.18, no, 2.18 times 10 to the 23rd, and now we're atoms of hydrogen. What would the ratio be for oxygen? 1 oxygen to every 1 H2O. So how many atoms of oxygen are there? Good. Any questions? Do we have followed that one? Oh, no, that's not a 0, that's an O. 1 oxygen. So that's oxygen. Oxygen. 1 oxygen. So part B, which we don't have time for today, says determine the mass of 7.92 times 10 to the 19th carbon dioxide molecules. So now we're starting at molecules, going all the way back to mass, so we'll just do the exact same thing, but going backwards.